In this lesson, I'm going to look at the code used when I need to create an array capable of holding the number of characters that I want to read from a file and into memory. Before you start on this, I'm assuming that you've already watched the previous video in which I went through the code in 01_read file, which is the project I'm looking at here, and you find that in the Step 10 code archive. Now remember, I could be working with a file of just about any size, and I can't know in advance how much space I need. That is, how long the array needs to be to hold the data that I'm going to read from the file. My code has to calculate the appropriate size based on the size of the file, and then it has to allocate enough memory to store that amount of data in the array. I do that here. I use the malloc function to allocate size amount of memory. Size, you may recall, gives the size of the data file in bytes or characters returned by the ftell function after the file pointer f has been moved to the end of the file here by fseek. The value of size is used to create an array, where b is a pointer to a character or an array of characters, and that array needs to be capable of holding the number of characters given by the size variable, like this. The malloc function returns a pointer to void, or in other words, it's a generic pointer that could, in principle, point to anything. And I cast this pointer, or in other words, I convert it to a character pointer. And now that matches the declaration of b. Not all compilers require this cast. Some will let you get away without it, but it's good practice anyway. Now, I'll have more to say on typecasts in the next lesson. Okay, so now I can fill my array b with characters by reading the contents of the file using fread. The arguments to fread are 1. b. This is the buffer or array into which the data will be read. 2. The size of each data item that I want to read, and here that's 1 for a single character. 3. Size. This is the number of items, here the number of characters to be read. 4. F. And that's the file pointer to the source data file. The returned value, items_read, gives the number of items that were read after the function has executed. Once I've read in the data, I need to close the file. And now I'm ready to process the data in memory using a for loop to iterate through all the characters in the array b from I equals 0 while I is less than size, incrementing line count whenever a new line character is found. And right at the end, I call free on the buffer b. The free function frees up the memory that was allocated with malloc. If I didn't free up that memory, it would remain allocated. That is, it would remain unavailable for use by anything else in my program. So even though I finish with my buffer b, once I exit the read-in function, the memory that I allocated, if I hadn't called free upon it, would still be in use, taking up space that I might need for other things later on. This brings me to the subject of memory leaks. Since my local variable b is no longer available to me once I've left this function, I no longer have any way of getting at that bit of memory from code outside the function. So I no longer have a variable that points to that memory location. And that's called a memory leak. In a short and simple program like this, a memory leak, a single memory leak, might not cause any problems at all. But in a large program, if you accumulate memory leaks, over time, your program may eventually run out of memory altogether, and it could cause it, at the very least, to go slow, or it could even crash. So, when you allocate memory that you no longer need, be sure to free it, and that's what I've done here. And now a word on garbage collection. This is something that you may be familiar with if you've programmed in other languages such as Java, C# or Ruby. Those languages, and many other languages, automatically free up unused memory in a process known as garbage collection. A programming language that does garbage collection relieves the programmer from the responsibility of freeing up memory explicitly. But it also introduces some performance penalties. Put simply, garbage collection can slow down your programs. The C language is often faster and more efficient than garbage collected languages, but you must be careful to manage memory yourself, and in particular, as I said in this lesson, be sure to free up memory that's no longer needed.